Good morning, everyone. Today, I will be presenting an important and fundamental topic in operating system, which is memory allocation, contiguous versus non-contiguous. So, what is memory management? Memory management is the backbone of any operating system. It directly affects system performance, application speed, and multitasking capability. In this presentation, we will understand how memory is allocated, why different strategies are used, and what advantages and limitations they carry. Now let's start with our first slide, which is understanding memory allocation. So let's begin with the basics. What exactly is memory allocation? So memory allocation is the process of assigning blocks of memory to programs or data for execution. Every time you open a software or run a command, it needs RAM, and the operating system decides how much and where. The goal is to optimize RAM usage, avoid conflicts between processes, and enable multitask. However, the challenge is to balance resource utilization with system flexibility and performance. Poor memory allocation can slow down application, can cause system instability, or even lead to crashes of your system. Now, start with our first topic, which is contiguous memory allocation. One of the earliest techniques used in memory management is contiguous memory allocation. In this approach, each process is given a single continuous block of memory, like a straight line of memory cells. There are three types of contiguous allocation. First is unified block. Each process receives a single and uninterrupted block. Second is fixed partitioning, where memory is divided into equal or unequal fixed size blocks at boot time. Next one is variable partitioning, where partitions are created dynamically based on the size of process at the runtime. This method is very easy to understand and fast to execute, which makes it ideal for simple systems like embedded devices or other operating systems. Next, we have the advantages and fragmentations in contiguous allocation. So, contiguous memory allocation is simple and efficient when system load is predictable. Let's explore its advantages. First is fast access. Since the memory is continuous, so address translation is quick. Second, the simplicity. The algorithm is straightforward and uses minimal OS resources, so it's simple. However, there are major downsides. First one is internal fragmentation. Internal fragmentation occurs when the process is smaller than the allocated block. For example, if there are partition of 5 MB and the process is 3 MB, so there is internal fragmentation of 2 MB. Next one is external fragmentation. External fragmentation occurs when small gaps of free memory appear between occupied blocks, making it hard to allocate space for large processes. Now let's imagine you have two partitions of 2 MB and both have two processes of 1 MB. So we and if another process of 2 MB comes, then we have 1 MB of space in both partition, but we cannot allocate the uh, ready process to the process memory block, so because it is already allocated by the another processes. So this condition is known as external fragmentation. To handle this, compaction is used, where the OS shift memory blocks to merge free spaces, but this process requires CPU time and slows down the systems. Imagine packing a suitcase but leaving gaps between items. Soon you run out of space even though it is not fully used, so that is fragmentation. Now next one we have non-contiguous memory allocation. Uh, to overcome fragmentation issues, modern operating system use contiguous. Modern operating system uses non-contiguous memory allocation. Here the process memory is broken into smaller pieces and stored in different memory allocation. They don't need to be side by side. This gives the OS more flexibility and enables it to better utilization of the memory. The two main techniques used in non-contiguous memory allocation are: first, paging. In paging, both logical and physical memory are divided into fixed size blocks. Next, segmentation. In segmentations, memory divides based on program structures like codes, data, or stack segments. Now let's go deeper in paging. In paging, logical memory is divided into pages and physical memory is divided into frames. Here uh, the size of page is equal to the size of frame. A page table maps each page to the frame. To speed up access, the CPU uses a cache called TLB, translation look-aside buffer. It is used to store recently accessed page entries. Typically, page size are 4 KB, 8 KB, or 16 KB. Paging solves external fragmentation because any free frame can be assigned to a process. It also enables virtual memory, allowing processes to run even when if they are not fully loaded into RAM. However, maintaining page tables adds overhead, and address translation slightly slows down performance. Now we have segmentation. Now let's understand segmentation. Unlike paging, segmentation divides a program into logical units like code, data, heap, and stack. Each segment is mapped through a segment table which contains the base address and limit of that segment. This provides a user-friendly structure and better access control, especially in shared systems. Segments can be independently protected and shared among processes, which makes it ideal for systems with shared libraries. But if segments are of different sizes, external fragmentation can still occur. So, which more intuitive segmentation needs additional handling by the OS. Now, advantages and trade-offs of non-contiguous memory allocation. Non-contiguous memory allocation offers benefits in modern computing, which are: first, it supports efficient memory usage by eliminating external fragmentation. Second, it allows dynamic growth of data structures like array or stacks. Third one, it enables virtual memory, which lets systems run large apps with less physical RAMs. However, the trade-offs includes page and segment table management adds overhead. Second, the access time increases slightly due to address translation. Third, operating system design becomes more complex. Despite these drawbacks, the advantages far outweigh them, especially in multi-user or multitasking environment. Now, next we have some real-world application and use cases. Uh, let's ta- let's take a look at where these techniques are used in the real world. First, we saw the real-world application of contiguous memory allocation. So, the contiguous memory allocation is used in first embedded system with fixed function and simple task. Second, bootloaders where small codes must run quickly. Third one is fixed size arrays or data structures in program. Now we saw non-contiguous memory allocation uses. So non-contiguous memory allocation is used in first modern operating system like Windows, Linux, and Mac OS. Second, server handling large databases or applications, like it uses in the server handling large databases or applications. Third one, it's used in systems supporting multiple concurrent users. Paging is essential for supporting virtual memory and managing large application efficiently. Now, to summarize, fixed partitioning is simple and fast, but it leads to internal fragmentation and inflexibility. Next, variable partitioning solves that, but introduces external fragmentation. Paging and segmentation, the non-contiguous techniques, are more flexible and efficient, powering modern OS today. Understanding how memory is managed gives us insight into how processes works behind the scenes and why certain apps run smoother than others. In the future, we will see trends like hardware memory virtualization, persistent memory, and NUMA supports continuing to evolve this field. Thank you for listening. I'm happy to answer any questions you may have.